Type 2 indeterminate forms include a product of 0 and infinity and a difference of two infinities. There are different approaches to evaluate such indeterminate forms. Learn them here in differential calculus. When evaluating a limit and the result turns out as 0 multiplied by infinity, we get a product of terms. When the result turns out as infinity minus infinity, then we get a difference. What could be the approach in order to find the answer in these cases when the L'Hopital's rule works on quotients? Remember that the rule guarantees an answer when the derivatives of the numerator and the denominator are determined. Let's dive into our first example, having the limit of x, ln of x, as x approaches 0. When we plug 0 for x, we get 0 times ln of 0. Take note that the natural logarithm of 0 is undefined, so we can't solve this further, thus we consider this as the third type of indeterminate forms. With two terms forming a product, we must find a way to have them transform into a quotient, so we can apply L'Hopital's rule. The first attempt is for us to try to place the first term, x, into the denominator. We do this by taking its reciprocal, then place that reciprocal into the denominator, so we do not alter the expression. We get the natural logarithm of x over the reciprocal of x, or that is ln of x over 1 all over x. Having a quotient, we can now apply L'Hopital's rule where we take the derivative of the numerator ln of x and the derivative of the denominator 1 all over x. In here, we have it transformed into x raised to negative 1 to easily use the power rule. So the derivative of ln of x follows the rule u prime all over u. In the example, that would be the derivative of x all over x. In the denominator, the derivative of x raised to negative 1 is negative 1 times x raised to negative 2 when we apply the power rule. Take note that dx all over dx is 1. From the numerator, the derivative of x is 1, so we get to write the whole expression as 1 all over x, all upon the negative of 1 all over x squared. From here, it is clear that we can cancel some of the denominators and flip them, leaving the expression with just negative x over 1, or simply negative x. It's time to plug 0 for x, which gives the answer as 0. Thus, the limit of x, ln of x, as x approaches 0, is 0. The second example has the limit of x times e raised to x as x approaches negative infinity. By plugging negative infinity as x, we have negative infinity times e raised to negative infinity, which can basically be rounded as 0, thereby having the indeterminate form of negative infinity times 0. And to use L'Hopital's rule, we place one term as a denominator. This time, we choose x, making the expression e raised to x upon the reciprocal of x. Then we are ready to apply the rule. So take the derivative of e raised to x and also the derivative of x raised to negative 1. Again, this is the reciprocal of x. Then we get e raised to x over negative 1 times x raised to negative 2. Or we can simplify the denominator to have e raised to x over negative of 1 all over x squared. Flip the denominator of the denominator up to reduce the expression as negative x squared times e raised to x. With the simplified expression, we now substitute negative infinity for x. So we have the negative of negative infinity squared times e raised to negative infinity. And this results to negative infinity times 0. From the first derivative, we still ended up with the same type 2 indeterminate form. Before moving further to higher derivatives, let us attempt to place the second term of the expression as denominator, that is e raised to x. So the expression turns as x upon 1 all over e raised to x. Continue with L'Hopital's rule. So take the derivative of x in the numerator and also the derivative of 1 all over e raised to x in the denominator. The derivative of x is 1, and the denominator can be transformed into the derivative of e raised to negative x. This denominator can then be differentiated as e raised to negative x times negative 1, and the expression can be written as 1 over negative e raised to negative x, or that is 1 all over 1 upon negative e raised to negative x. Further simplify this as negative e raised to x. Now plug x as negative infinity, making the function negative e raised to negative infinity, which is 0. So, the limit of x times e raised to x as x approaches negative infinity is 0. The next example is to evaluate the limit of secant of 7x multiplied by cosine of 3x as x approaches half of pi. By testing x as pi over 2, we have secant of 7 times pi over 2 with cosine of 3 times pi over 2, which eventually gives infinity times 0. With the product, we make one term as denominator, and we choose secant of 7x. The function then turns into cosine of 3x upon the reciprocal of secant 7x. Also recall that the reciprocal of secant x is cosine of x. Thus, we can write the equation as cosine of 3x over cosine of 7x. Now we apply L'Hopital's rule. So take the derivative of cosine 3x and also the derivative of cosine of 7x. The derivative of cosine is negative sign times the derivative of the unit 3x. In the denominator, we also get negative sign of 7x with the derivative of 7x, where the derivative of 3x is 3 and the derivative of 7x is 7. The equation turns as 3 sine of 3x over 7 times sine of 7x. With x as half of pi, the equation turns into 3 times negative 1 upon 7 times negative 1, where the negative 1's can cancel out. Thus, the limit of secant 7x with cosine of 3x as x approaches pi over 2 is 3/7. The next example illustrates an approach to evaluate the difference of infinities. Take the limit of x less the root of x squared minus 1 as x approaches infinity. If we plug infinity for x, we get infinity minus the root of infinity squared minus 1, which results to infinity minus infinity. In this case, since we have two separate terms, we cannot work on making a denominator nor use L'Hopital's rule. The approach for this case is with conjugates. Multiply the conjugate x plus root of x squared minus 1 to the function, and get the quantity of x minus the root of x squared minus 1 times the quantity of x plus root of x squared minus 1 all over x plus the root of x squared minus 1. Using the conjugate, we get difference of two squares in the numerator, and we can simplify this as x squared minus the square of the root of x squared minus 1. This then can be written as x squared minus the quantity of x squared minus 1, and also further simplified as x squared minus x squared plus 1, all upon x plus the root of x squared minus 1. From here, we can clearly cancel x squared in the numerator and get 1 upon x plus the root of x squared minus 1. With x as infinity, we have 1 upon infinity plus the root of infinity squared minus 1, where the denominator still can be reduced to infinity. Thus, the limit of x minus the root of x squared minus 1 as x approaches infinity is 0. Example 5 has the limit of 1 over x minus 1 upon sine of x as x approaches 0. With x as 0, we get 1 over 0 minus 1 over sine of 0, which then is solved as infinity minus infinity. Without any radicals, it is not wise to use conjugate for this case, but we can still evaluate the function using least common denominator. Determine the LCD and coin the two terms together as sine of x minus x all upon x times sine of x. As x is equal to 0, we get sine of 0 minus 0 all over 0 times sine of 0, which is basically 0 all over 0. Now we are back to type 1 determinate form where we can use L'Hopital's rule. Take the derivative of sine of x minus the derivative of x all over the derivative of x multiplied by sine of x. Again, the derivative of x is 1, so the numerator has cosine of x minus 1. The denominator contains two terms, thus we use product rule, giving x times the derivative of sine of x plus sine of x times the derivative of x. Here again, the derivative of x is 1, so we have cosine of x minus 1 all upon x cosine x plus sine of x. Now with x as 0, we have cosine of 0 minus 1 all over 0 times cosine of 0 plus sine of 0, which becomes 1 minus 1 upon 0 times 1 plus 0. We still ended up with 0 over 0 for the first derivative. So the next step is to take the second derivatives of the terms. From the first derivative equation, we take the derivative of cosine x minus the derivative of 1, and everything is over the derivative of x cosine x plus the derivative of sine of x. We eliminate the derivative of 1. So we get negative sine of x all over x times the derivative of cosine x plus cosine x times the derivative of x plus cosine x. Since the derivative of x is 1, we can simplify the cosines in the denominator and get negative sine of x upon negative x sine of x plus twice of cosine x. Placing 0 for x, we get negative sine of 0 over negative 0 times sine of 0 plus twice of cosine 0. This is simplified as 0 over 0 plus twice of 1, which gives 0 over 2. So, the limit of 1 over x minus 1 all over sine of x as x approaches 0 is 0.